Okay. Now, first of all, notice that the formula AO2O3 already has two aluminums in it. So just take one molecule, we'll have two aluminum atoms. I'll write a 2 on the left-hand side. Yeah, we've taken two aluminums on both sides. Now notice the oxygen is a little bit tricky. Okay, we want three oxygens on both sides. Well, the formula Al2O3 already has the three oxygens, but to get three oxygens on the left, we have to use a fraction. So 3/2 times 2 will give us a total of three oxygens. Now, I personally don't like fractions in my balance equation. I will accept them on exam, it's fine. You know, remember in thermo, we deal with moles, that's fine. But I would actually personally suggest, I would like it better if you actually doubled everything and make this a 4, make this a 3, make this a 2. But if you can balance it with fractions, that's fine also. Okay, now notice I've also labeled the aluminum Ra. What does Ra stand for? It stands for reducing agent. Okay, now what's the logic behind that? Well, the logic is that the oxygen was reduced from 0 to -2, and aluminum was the agent that did the job. Okay, and what does OA stand for? It stands for oxidizing agent. Was oxygen really the oxidizing agent? Yeah, it made the aluminum go from 0 to +3. It oxidized the aluminum. So I'd like to be able to label the agents also.
Professor?
That is, everyone's okay.
Professor?
Yes,
So the oxidizing agent reduces the oxygen. Is that what you're saying?
no, the oxygen actually oxidizes the aluminum.
Okay.
So the aluminum goes from 0 to +3, so it is oxidized. Who did the job? The oxygen. Because the aluminum reacted with oxygen, it was oxidized. So oxygen was the agent that caused the aluminum to be oxidized. If that seems too complicated, here's another way to look at it. What happened to the oxygen? It was reduced, right? Oxygen went from 0 to -2. So up here in blue I marked the oxygen is reduced. So if it's reduced, it's the opposite kind of agent.
Okay.
So if oxygen is reduced, it must be the oxidizing agent. If aluminum is oxidized, it must be the other kind of agent. It's the reducing agent. I know it's kind of tricky. It's kind of complicated. What do you think, Lottie? Got the basic idea? Not too bad?
Yes. Thank you.
We'll practice some more and some others coming in. Okay, so we're looking at a complicated reaction here. Now, you can save yourself a lot of time if you suspect an element is changing state and just look at that one first. For example, look at nitrogen. Nitrogen is not on the rules of priority. If it's not on the rules, it probably is going to change state. So let's look at nitrogen on both sides. So looking at NO2, oxygen is assigned first at -2. Here's our worksheet below. So 2 times -2 gives a total -4. To make it 0, nitrogen must be a +4. One nitrogen, so it must carry the charge. So on the left-hand side, nitrogen is a +4. Now look at nitrogen on the right-hand side. Hydrogen has priority +1. Oxygen had priority -2. So that one, look at the worksheet below. So that one hydrogen gives a +1. The 3 oxygens give us a total -6. Charge is supposed to add up to 0. Conclusion, look in green, look at the green. The nitrogen has to be a +5 to make this 0. There's one nitrogen, so it has a +5 state. So I made a good guess. Nitrogen went from +4 to +5. So looking at the next line, nitrogen goes from +4 to +5. That is oxidation. And summarizing, that's a change of 1 electron per nitrogen. Well, going back to the original problem now, we have to find the other element that's changing state. Well, it turns out chlorine actually changes a lot. So let's look at chlorine on both sides. So looking at HClO, hydrogen has the +1, oxygen -2. Looking at the worksheet below, to make this 0, conclusion chlorine must be a +1. Now looking at HCl, hydrogen has priority +1, forcing chlorine to be a -1. So chlorine goes from +1 on the left-hand side to -1. So the summary of that, I put a bracket here. So chlorine goes from +1 to -1. That's a change of 2 electrons for chlorine. Okay, look at the red boxes now. We've got to get the electron exchange equal. So what do the numbers 1 for nitrogen and 2 for chlorine suggest? Switch the numbers. So if we take 2 nitrogens and 1 chlorine, we'll have a 2 electron exchange, conservation of electrons. Now remember remember, the red box are if statements. If we can really, really do this, then we'll have the electron exchange equal, and we'll have the equation almost balanced. That would be the hard part of balance the equation, is to use those numbers in the boxes. So how can we get two nitrogens on the left-hand side? Yeah, so I wrote a 2 here and a 2 here to get the two nitrogens. How can I get one chlorine on both sides? A 1 here and a 1 here will get the chlorines to balance. Now, sometimes a little bit of cleanup to do. For example, notice we're depending on water to make sure the oxygens and hydrogens balance. For my experience, go for the oxygen balance first. So notice on the right-hand side, we have 2 times 3, a total of 6 oxygens. And so we have 1 here, 2 times 2, 4 here. That's 5. Yeah, we need 1 water molecule to get 1 oxygen. Now keep your fingers crossed. If things are going well, the hydrogen should be balanced too. Let's see. So we have 2 hydrogens from water, 1 more from here. That's 3 on the left. And we got 2 plus 1, 3. Yeah, so this is a completely balanced equation. Okay, look at the agents. Let's see if the agents make sense. So notice that the nitrogen is oxidized. So therefore, it's the reducing agent. By the way, notice the whole chemical, even though nitrogen is the active ingredient, the whole chemical NO2 is called the reducing agent. Okay, now look at the chlorine. The chlorine was reduced, so it must be an oxidizing agent. And again, the whole chemical is the oxidizing agent. Well, by the way, here's kind of a side thing you don't have to know. HClO is called hypochlorous acid, and you use its cousin in the laundry. Sodium hypochlorite is the active ingredient in bleach. Now, how does the bleach do its job? It doesn't do its job because bleach has chlorine in a very unusual oxidation state. It's in a +1 state, okay? Very unstable. Matter of fact, it immediately will break down to give you some chlorine gas. And that's why bleach has that odor to it. And then finally, it'll go from +1 to -1, okay? So notice bleach is an oxidizing agent. Why do you want to put an oxidizing agent on your clothes? Because when you oxidize a stain, it usually changes the color. Again, nothing you need to know, in terms of the course, but I thought you might be kind of interested. Okay, so I'm very suspicious of nitrogen. It's not on the rules of priority. So let's concentrate on nitrogen first. So in this first compound, oxygen has priority, -2, but there's 2 of them, giving us a total of -4. And to make this 0, nitrogen must be a +4. Okay, now look at this first compound on the right-hand side. Hydrogen has priority, +1. Oxygen next priority, -2. Look at the work below. So +1 for the hydrogen, 2 times -3 and -6 for the total oxygen. To make this 0, the nitrogen's got to be a +5. So nitrogen goes from +4 to +5. I'll just draw a bracket for a moment. So that's the oxidation. Now, I don't get it. Where's the reduction? Help. Anyone see it? Look at the second compound with nitrogen in it. Okay, oxygen has priority at -2, forcing nitrogen to be a +2. Now this is really weird. Look at nitrogen is oxidized from +4 to +5, but it's also reduced from +4 to +2. Now, rather than have 2 brackets off the same chemical, I'd like to notice what Berg decided to do in the next line. I'm going to write NO2 twice. Okay. Now, in both cases, it's +4 to begin with, but notice I draw a bracket from the first NO2 to the first compound HNO3, and a second bracket from the second NO2 to NO. In other words, I'm just going to almost pretend like the chemical NO2 is like 2 different chemicals, okay? And that'll make it easier to work with. Okay, so let's summarize the first NO2. It went from +4 to +5. That's a change of 1 electron per nitrogen. Look at the second NO2. Nitrogen went from +4 to +2. That's a change of 2 electrons for those nitrogens. Now, what do the numbers 1 and 2 suggest to you? Switch the numbers. Take 2 nitrogens in this red box and take 1 nitrogen in this red box. And that's because 1 times 2 will give you 2 electrons lost, and 2 times 1 will give us 2 electrons gained. Now remember, the red box is the key. Those are like if statements. If we really can take those numbers, we'll have the electron exchange equal, and we'll almost have the equation balanced. It'll give us the hardest numbers and balancing. So look at the numbers below. So I took 2 NO2s here and 2 HNO3s. That's how I got the 2 electron exchange there. And 1 NO2 and 1 NO, and that gets 2 electron exchange there. Okay, now we're depending on water to balance the oxygen hydrogen. So let's see how this is working out. Let's see, on the right-hand side, I have 2 hydrogens. So to balance the hydrogens, look, I need 1 water. And how about the oxygen balance? Let's see, on the right-hand side, it looks like I have 6 plus 1, 7. I've got 4, 6. So 1 water ought to do the job. So that should be the balance equation right there. Now, what's kind of weird is labeling the agents. Okay, this first NO2 was oxidized, so it would be the opposite kind of agent, reducing agent, and the second NO2 was reduced, so it must be the opposite agent as an oxidizing agent. So notice NO2 is both the oxidizing and reducing agent. Kind of weird, isn't it? So what actually happens in solution is NO2s hit together and they give you these different products taking place. So actually in a bottle of NO2, they bump together, and when they do, you get this weird reaction taking place. Any questions on this particular one? So the moral of the story is if you ever have a chemical that is both changing electrons, gaining and losing, my suggestion is break it up into writing it twice. And if you want to, you can combine at the end. If you wanted to, you could say well, there's 3 total NO2s. I think it's easier just to leave it broken up like this. Okay, you're now ready for mini super killer. Now, the reason I call this one mini super killer is because up until now, we've had neutral molecules. Now notice that MnO4 has a negative charge on it. On the right-hand side, MnO4 has a negative 2 here. That's not a mistake, by the way. It's negative 1 on one side and negative 2 on the other side, and the hydrogen is a positive charge. So now we're going to balance what's called an ionic equation. Just a little bit trickier, but not too bad. Okay, first of all, who's changing state? Who are you suspicious of? What elements? Yeah, manganese is not even on the list of oxidation states, so it's going to change, yeah. Matter of fact, the transition metals are all over the place. They're going to change. Okay, so let's figure out the manganese on the left-hand side. So oxygen has priority, negative 2, but there's 4 of them, total negative 8. Okay. Now notice in this case, the charges are not add up to 0, they're going to add up to negative 1. Okay, so therefore, the manganese would have to be a plus 7 to add to a negative 8 to make it a negative 1. So manganese on the left-hand side has a plus 7 oxidation state. Okay, let's check out manganese on the right-hand side. Okay, oxygen again has priority negative 2. There's 4 of them, total negative 8. Charges have to add up to negative 2. So manganese would have to be a plus 6 to make the total negative 2. So manganese is a plus 6. So yeah, manganese is changing from plus 7 to plus 6. Yeah, so it's going to get a bracket. Okay, now I wasn't sure who is going to be oxidized. But what I noticed on the right-hand side, you've got oxygen all alone. Remember, an element alone is 0. And on the left-hand side, it's in compounds. Now, I figured the easiest one to do would be to analyze it in water. So in water, oxygen has priority negative 2. So oxygen goes from negative 2 on the left to 0. Okay, so I'm going to show you the next line. So now I have my bracket. So kind of a summary where I'm going to go. So manganese from plus 7 to plus 6, that's a change of 1 electron per manganese. And oxygen goes from negative 2 to 0, that's a change of 2 electrons per oxygen. What do the numbers 1 and 2 suggest to you? Switch the numbers. Okay, now notice in the boxes though, I didn't write a 2 and a 1. Why was that?